of an example of a non-torsion free, well, I'm sorry, of a torsion free but non-flat module. I think this is something that I stated, but I didn't prove. And this guy was given as follows. We've taken a field K. It's a field. Our ring R is the ring of just polynomials in two variables. And an ideal for R, which is in particular an R module, therefore, was the ideal generated by these two guys, side of R. So this is an R module. And, well, we have this obvious sequence that this ideal sits inside of R, and the quotient is the field. Okay, so this is R mod I, and this is an exact sequence of R modules. Now, the trick was that we have a projective resolution of this K, and this projective resolution was given by viewing this K as an R mod I. This was given by the fact that this X and Y was a regular sequence in R, and this was given as follows. We took R, took two copies of it, we mapped it to R, and this map sent A and B to AX plus BY. Oh, yeah, I guess AB to AX plus BY. So the image of this thing is clearly the ideal I. So if I look at this quotient, then the kernel of this map is I, which is the image of this map, and the sequence is exact here. And then here I put wedge 2 of R2, which is R. But remember, the exercise was to use that this is wedge 2 of R2 to do this in general. And the map from here to here was something that sent A. Well, I needed to give you something so that I could kill it here, and I would send it to A, Y, AX. And then probably I needed a minus sign somewhere. So you can put a minus here and then keep the plus there, or you put a minus here and put the plus there, it doesn't matter. And this sequence was exact. Again, it's a sequence of R modules, but now you see that this is a resolution by free modules of K. So this is a resolution by projective modules of K, and this allows me to compute Tor for this K. So this allows me to compute Tor star of, I guess, of anything, of K with any module B for the ring R. And I could use this resolution. Let me call this resolution K. So this complex that has three terms, I'm going to call it K. And this comes with a map to R mod I. So this is given by taking the homology of the complex K dot B over R. So that's how we computed the Tor groups. We took a projective resolution of the thing that we wanted to compute Tor by, and we tensor with the other factor. Okay, so now I have this sequence of R modules, and that sequence of R module gives me the following sequence. So it says that, well, let's take Tor of this thing with any module B. Okay. So I'm going to take Tor 0 of this guy with a module B. So that's just K tensor over R with a module B. This is tor 0 of this guy. So this is R tensor R over the module B, which is just B. And this is just B divided by I. B. Then we have, well, tor 0 of I tensor over R B, so forth. So now I'm going to have tor 1 of K B. Everything is over R. And here's the trick. So the first thing, well, here I have tor 1 of RB, but R is free as an R module. So tor 1 is 0. R is projective. So this guy is 0. And now that 0 is here. And I have tor 1 of I B. And now I have tor 2. Okay, B. This is over R. And now I have tor 2 of RB, which is 0 again, because R is free. So in general, we see that this is going to continue happening. And I'm going to have that tor K R of IB is isomorphic to tor K plus 1 R of KB. Okay, so now you can compute this tor of K with anything using explicitly this resolution. And you can check that there's a tor 2 that is non-zero. So compute. For any B, you can do this. But do it for some B such that that is non-zero. So, okay, so what are we looking for? We're going to take this guy, tensor it with B, and compute this homology of that thing. So that's going to look like B, B square, B, 0 before, 0 is like that. And the maps from here to here, again, the same thing is now I'm going to have some A, B that get mapped to, I should have been careful. I think I said R modules, and I am multiplying by X and Y here. I need to be careful if R is non-commutative, where I am multiplying by X and Y. But in this case, R is commutative. So I don't care about this order of these things. I have B, Y. And here, same argument. If I have A, it maps to AY minus BX. So what you see immediately is that you can find things such that this map has a non-trivial kernel. So pick some module, some R module, P, such that the kernel of the map from A to AY minus, what did I do here? minus AX. God damn it. Comma. Is non-zero. So that means in particular you're looking at some module over R such that multiplication by X and multiplication by Y are 0. For example. If you do this, then anything is going to be in the kernel. So for example, we could take, could be R over I itself. So this guy is non-trivial, is K, and as a module over R, multiplication by X and multiplication by Y are 0. So if with this choice, the kernel of this map is the whole of B. In this particular case, the kernel of that map, let me call this D2, is equal to K, which is non-zero. And this is the Tor2, by definition, of, well, in this case, we've done K over R. But by this thing that we've proven here, this is the same thing as the Tor1 over R of IK, which is non-zero. So this implies that I is not flat. Okay. For flat guys, they were acyclic for Tor. Okay, so that's one example that I said I was going to do in detail, but then now you can figure out that this is true for any finite regular sequence. The top Tor is going to be, so if you give me a ring and a bunch of elements, n elements, I've given you a complex that was the Koszul complex, and the top Tor is going to be of degree the number of elements that I've given you. And it cannot be 0. Same argument. So any complete intersection, so this is a point in, this was geometrically given by a point in the plane that was given as the intersection of two lines. So this is the line x is equal to 0 or y is equal to 0, and it's given by this point. And the ideal defining this thing is non-flat. And the top Tor is how many lines you needed to describe that intersection. Okay. So you can guess what is the analog of that situation in higher dimensions. All right. So that was one example. The other thing that I said I was going to prove is the following statement. Is that it was this theorem. So the statement was that if, let's say that you have a ring R, and you have two R modules, well, I guess not two R modules, but you have an R module, I think I was using N, and then mod R M, then suppose that you give me a flat resolution of M, in mod R, then Tor R dot of M n is the same thing as the homology of the complex that you obtain by taking this tensor product. I mean, of course, if the resolution is if the resolution is by flat guys that are projectives, then yeah, that's by definition. Okay? So the statement here is that I can take this flat to be non-projective. Oh, yeah. So before doing that, I guess I should have given an example of a flat module that is not projective. So this is an example of something that is non-flat and is torsion-free, because we've already proven that when the ring R was Z, then being torsion-free implied flatness. So for abelian groups, flatness was torsion-free. But there are examples of modules that are flat and are not projective. So examples of a flat module and non-projective module. So the canonical example of such a thing is to take the ring R to be just the integers and the module, let's say F, to be the rationals, or the rationals divided by Z. So this guy here is flat and not projective. So let's prove that. Or take Q over Z. Yeah, so there's a few ways of proving this. Let's walk through them quickly. So I don't remember if I've given this, but so let me state it. Someone tell me if I've already proven this. But if you have P a projective module, implies that P is a direct summand of a free module. Unfortunately, free and flat also start with the same letter. Direct summand of a free module. That means that there exists, so i.e., there exists a module M such that P plus M is free. Did I prove that? Obrigado. All right, so okay, so I claim that Q is not projective. I cannot sum something to get a free Z module. So it's clear that Q is not free also as a Z module. And the statement there is, I guess the most general thing that I can state here is the following: is this beautiful property of principal ideal domains. So Z is a principal ideal domain. And projectives over a PID are free. And the way you prove that is, again, the same thing. You just use that, use that any projective is a direct summand of a free module, and now use something like the Chinese remainder theorem that holds on a PID. So exercise, check this statement. Check this arrow here. And then this together with Q is not free. So I don't think I've given this definition, but another way of viewing this is Q, let me not give this definition because we're not going to use it. But Q is a divisible Z module, meaning that whenever you have an element here and a non-zero divisor in Z, well, in Z anything is a non-zero divisor, then there exists another element in the module such that that non-zero divisor by this other element gives you your guy in Q. So that's the definition of a module being divisible. Z is not divisible as a Z module. Therefore, any free module is not divisible as a Z module. because every free module is going to be direct sums or products of z's. And, well, so Q cannot be free. Because Q is divisible and Z and the free modules over Z are not divisible, never divisible. Okay. All right, so that justifies why this theorem is interesting, because we can use flat modules that are not necessarily projective. So let's prove this theorem. Okay, let's check this. So how do I compute this guy? We take a projective resolution of M. And probably I'm not going to use this projective resolution. So let's forget about this projective resolution because I don't think I'm going to use it. Let's compute explicitly what that side is. Okay, so I'm going to compute this homology. So what I'm going to have is this guy. I'm going to have F0 that maps to M. This is not part of my complex. I have F1 and so forth. And I'm going to take the tensor product of this flat resolution with N. So the first term is F0 tensor N. This is over R. And then I have F1 tensor N, again over R. And the homology in degree 0 is the kernel of this thing, which is everything, modulo the image of this map. Okay, so it's this object modulo the image of this. So what we see is that H naught of F dot tensor N over R is F naught tensor over R with N divided by the image of F1 tensor over R with N. But on the other hand, I could have taken this whole sequence and tensor it with N. So the first term would have been this. And, well, I have no clue what happens after this, but tensoring by N is exact on the right. So this sequence here is still exact. So that means, I mean, this was an exact sequence. This was a long exact sequence. But this one is exact now here in the category of just Z modules. So that means that, well, the kernel of this guy is everything. So the image of this map is everything here. So that means this guy is surjective. And the image of this guy is equal to the kernel of this guy. That means that, well, this divided by the image is the same thing as this guy divided by its kernel, which is the same thing as M tensor with N. And M tensor with N, we know, is tor 0 over R of Mn. Either by the same argument, if I had used P, a projective resolution instead of a flat one, or just the fact that remember that these guys were defined as the left-derived functors of a right exact functor, which is the tensor product, and the zeroth derived functor is equal to the functor. So that theorem is true in degree 0. I guess I can just start from here now. Okay, so let's move on to degree 1. So what's the trick now? So I'm going to look at my complex. This flat resolution complex consists of these guys, F1 and everything. F2, and so forth. So I can just truncate this complex here now. And now, this is a complex. So this is a complex. Well, this guy here was exact everywhere except at 0. Now this one is also exact everywhere except at 1. And, well, what is the homology of this complex in degree 0? Okay. So the homology of this complex in degree 0 is F1 modulo the image of F2. So the homology of that complex in degree 0 is F1 divided by the image of F2. But this guy here was exact. So we're using the same argument as there. F1 divided by the image of this guy here is the same thing as, well, let's look at the kernel of F1. Okay? So how do I identify this kernel? So this is F1 divided by the kernel from F1 to F0. And then again, since the whole thing was exact, this was a resolution of M. Then what I could do is just look at this. F0, and then here I have the kernel. And then by this argument here, I realize that this complex here is a resolution of K. So this is exact. So that's a resolution. And it's a resolution by flat modules. Right. Okay, so I need to compute the homology in degree 1 of my original complex. So I need to compute H1 of this guy. So what is that? What is H1 of this complex F dot tensor with N? Well, so I'm going to look at F1 tensor with N, mapping to F0 tensor with N, the kernel of that, modulo the image of, this is, I can look at the kernel from F1 to F0, but I already know what that is, because this F1 to F0 factors through this map to K. Okay. And then I need to divide by the image of F2 tensor with N. So right. So what I want to prove eventually is that this is tor 1 of M N over R. That's what I want to prove. And what I've done is to check that this is the same thing as, well, I want to check, this is by definition, the kernel of F1 tensor N to F0 tensor N modulo the image from F2 tensor N to F1 tensor N okay, and now I want to exploit the fact that I have this sequence and this guy is flat. Okay, so let's look at this sequence. That was our defining sequence to get this resolution. We have n. I want to compute tor of this guy with n. And I know that this is a cyclic for tor. So tor of this guy with n is 0 in degrees higher than 0. And then I don't care about this because I'm going to use induction and I'm going to take a flat resolution of this guy. So let's look at this sequence. And that sequence there gives me the same thing that we just did about 20 minutes ago. M tensor R n. This is tor 0. Mn, I'm sorry for being so slow, to tor 0 F0 tensor with R, tensor n over R, tor 0 of the other guy, K, R with n, tor 1, and this is what I want to understand. The tor 1 of m n over R. And now I have tor 1 of this guy, which is 0. This is because this is tor 1 of f naught n. And f is flat by assumption. In general, I'm going to get, well, that 0 is that 0 there, and I'm going to get tor 1 of m, no, sorry, tor 1 of k n, and now I'm going to have tor 2 of m n, and tor 2 of f n, and in general I get isomorphisms between tor k of k n and tor k plus 1. So that's true whenever k is bigger or equal than 1. This is not true for k is equal to 0. For k is equal to 0, we have this sequence that this guy is the guy that I want to understand, and this guy is exact. The sequence there is exact. Okay? This was a long exact sequence. So this means that the kernel of this guy is equal to the image of this guy, and this map is injective. So I want to understand the image of this guy here, which is the kernel of this map from k tensor n to f naught tensor n. But now, I realize that if I kill the image of f2, this is exactly that. This is the kernel of k tensor n to f naught tensor n. So this isomorphism is checked. And now I can exploit these ones, because those guys I have for free for k bigger or equal than 1. So for k bigger or equal than 1, so starting from tor 2 mn, now I know that this is the same thing as tor k kn. Let's not remove the statement of theorem. No, but it doesn't matter. Or just that side. So we've proven the statement for tor 0 is the same thing as h0. We now have proven the statement that tor 1 is the same thing as h1. And now I'm missing tor k for k bigger or equal than 2. So now I know that for tor 0 and tor 1, I'm done. And I need to prove that tor k mn is isomorphic to the homology in degree k of this complex where k is bigger or equal than 2. But on the other hand, using that theorem, I realize that this is the same thing as tor k minus 1 of this complex k n over R. And now I can use induction in K. For lower values of K, I can assume that I can resolve this K by a flat resolution. So this is H K minus 1 of a resolution well, let me use a tilde here. This guy, F tilde, is any flat resolution of K. I've already proven it for 0 and 1. I want to prove it for higher K, so let's assume that I already proved it for K. Let's assume that I've already proved it for K minus 1. Let's prove it for K, which is what I'm missing. Okay, so I need to use only a flat resolution for K, but that's exactly what I started with. So the resolution that I took for M gave me a flat resolution for that K. And the homology in degree minus 1 of this complex is equal to the homology of degree n of this complex. So this is the homology in degree k of this complex, which is what I wanted to prove. Okay. Notice that there's only the subtlety that I need to be careful that I am computing these homologies in degrees starting with at least this degree 2. So that the kernel of this map modulo the image of this map, it doesn't matter if I do this for this complex or if I do this for the larger complex. Okay. All right, so that told us that I can compute Tor by flat resolutions. And this is true in general. You define Dolbeault resolutions by resolving your sheaves by injective modules, and then you can just replace those injective by Flask sheaves, which are not injective, but they are acyclic for the homology that you're interested in. You define any homology theory that you define as the derived functor of your given favorite functor. In this case, it was a tensor product. It could have been something else. Then you can compute these derived functors by taking resolutions by acyclic objects for your functor, not necessarily by projective nor injective objects. That I think we are going to prove eventually. Okay, so let's finish up with Tor. What are the things that I wanted to say about Tor? So I guess I wanted to say this. So the example I have in mind is I have a space X mapping to a space Y, let's say F, and I want to have a module over Y and a module over X, and what I could do is pull this module from Y to X and then tensor it with X on tensor it on X. So that's one thing that I want to do. And I want to understand the structure of this guy. So it's even easier if I have two modules here. Let's say that I have M and M prime. Then I could do two things. I could look at M tensor M prime and then pull it back to get a module on X. Or I could just take the pullback of M and then tensor it with the pullback of M prime and see what I get. So So now the statement is that these two things, the statement in geometry is that pullback commutes with taking tensor product. So these two things are the same. But what makes it interesting is that this is derived the same as well. If I take the derived tensor product here in x, in y, or if I take the derived pullback of f, then I get the same thing. So let's work towards proving that statement. Okay? So I'm going to stick first to this statement here. And let's look at this being the spectrum of some ring, R, and this being the spectrum. Let's probably do this the other way around. S, and this, because my base ring always has been R so far. So then this F corresponds to a map from R to S. It doesn't need to be injective, I'm sorry. Okay. So, okay, and now I'll forget that these rings were commutative so that I could take the spectrum. And let's just take arbitrary two rings. Okay? So let's take a morphism of rings, R to S, and I'll add the assumption so that this statement that I made here is factually true. Let's suppose that S is flat over R. Okay, so S, this is a morphism of rings. S is a flat R module. So in geometry, if you have a map of spaces like this, you say that X is flat over Y if locally the ring of functions on X is a flat module over the ring of functions on Y. Which in this case, there is both of them are affine. This is a global statement. If S is flat over R, then X is flat over Y. This is because flatness commutes with localization, and that I'll prove in a second. But let's get to that later. Let's do the global statement first. I'm sorry, the local statement first. Okay, so we are in this situation. We have a morphism of rings, and this guy is flat over this. Okay? And let's now take modules accordingly. So we're going to take M is an R module. And I'm sure I'm going to get this wrong. So M is an R module. And let's take N, an S module. One on the right, the other one on the left. I mean, this didn't require these rings to be commutative anywhere. Now, whenever I have an S module, it's automatically an R module. But what is not trivial, well, what is not true is that any R module is automatically an S module. I need to pull it back. So that was this pullback F, pullback there. So one thing I could do immediately is look at N, which is an S module, as an R module. And I could look at M, N, and take the Tor on the ring R. So this is view N as an R module, take the tensor product, the derived tensor product. So this is grab something here, pull it back. Oh, the other way around. I'm sorry. So I have this guy here. So this is just extension of scalars. All right, so that's one thing I could do. The other thing I could do is grab M and view it as an S module by tensoring with S. I could grab M, tensor it over R with S. Now this is an S module. And now I could just take the Tor with N. But now this is the Tor in the category of S modules. Now these are abelian groups, and these two are isomorphic. Okay, so let's prove that. Okay, so how do we prove this? So to compute this store here, I'm going to use a projective resolution of M, or a flat, no, actually, this time I'll use a projective resolution of M. So we take a projective resolution of M in the category of R modules. Modules on the right. So this is a projective resolution. And this side here is computed as the homology of P tensored with N. So that computes this store here. This is store R M N. This tensor product is over R. Now, this guy here, to compute this store on S, I need a projective resolution of this module over S. So now I claim that P tensor over R with S is a projective resolution of that module, of M tensor over S R is a projective resolution of M tensor over S. Well, the fact that it is a resolution is trivial, because tensoring by S is exact because S is flat over R. Right? So the fact that it's a resolution is because S is R flat. So therefore, tensoring over R with S is exact. So if I took the resolution from P to M and I tensored that thing with S, this still is still exact. Okay? So we have a resolution. And now why these guys are projective? Well, same thing. If you have any surjection and a lifting from P, then, so now I'm looking for a surjection at the level of S modules, just tensor this over S, that surjection, and you're going to get the same thing. Okay? So these guys are projective. Because liftings any lifting of S modules of works. Okay, so now this guy here is the homology of, well, that's not true. The other side that I want to compute over S, M tensor R S N, this is the homology of that projective resolution of P tensor R S tensor over S now with N. And the only thing to realize is that these two things are isomorphic. Okay? So this, well, let's put something in the middle between these two. This is the homology of P tensor over R with S tensor over S. Okay? And this is obviously isomorphic to that. Okay. So now let's use that lemma and let's grab this lemma and let's put our module N to be the push forward, well, sorry, again, pullback of an R module itself. So N is an S module, but let's take an S module that is of the form taking a tensor product by S of an R module. And this requires some work. So I would want to do something like this. I would want to have N to be something like S tensor over R with N. And I would want that guy to be an S module. But then now yeah, so, but that works, so it's fine. So this is an S module now on the, this is an S module now on the left. And that theorem there says that tor dot on the ring R of M with S tensor over R with N is the same thing as tor for the ring S of M tensor. Now it's on the other side with S over R with S tensor over R with N. So that's what this theorem says. Now M and N are both R modules. So here M is an R module, and N is an R module. Okay. So now let's take R to be commutative. So there's a big difference on tor for commutative rings. Well, this is the difference, right? So this guy is just an abelian group when M is a right module and N is a left module. This is just an abelian group. But if R is commutative, this is also an R module. So the functor tensoring by N lands in R modules, or the functor tensoring by M lands in R modules. So therefore, the derived functors for these functors land in R modules. And you can check that the derived functors for these functors are the same as you can compute those derived functors by computing them as derived functors to abelian groups, and the corresponding target is naturally an R module, just the same thing as this. So how do you compute this tensor product? You just compute the usual tensor product as if this ring was not commutative, and it just happens to be an R module. Okay? So that abelian group is an R module. The same thing for tor. So tor R Mn is an R module. So this happens when R is commutative. So that's something like this. So if I have two modules here, M and M prime is N. I have two R modules. I can take the tensor product. I can take the derived tensor product. That's just the tor of those two guys. And now let's just pull it back. So pull it back would be tensoring with S. So now I have this S, which is an R module. And I can tensor this guy over R with this guy, which is an R module. Okay. All right, and I claim that this is the same thing as taking the tor on S of the pullback of the two guys. So that's that identity that I said there. And now it makes it clear when that happens when this S is flat as an R module. Because to prove this lemma, we needed flatness for S as an R module. All right, so what I know is this, and what I want is this. Well, so I need to understand how do I compute this. And again, I take a projective resolution of M, and this thing here is computed as S tensor, the homology of P tensor N. But this S is exact. Tensoring by S is exact as an R module, so it commutes with homology. And, well, that's just this by the lemma. Okay. Have some time. Okay, so we have this pullback under flat morphisms commutes with tensor product. So that's a nice geometric property. What am I missing? Okay, yeah, so something I said before. It's localization. Crap. All right, so localization. So let's suppose that you have a ring R. R is a ring. This doesn't need to be commutative, but let's take S inside of R, a multiplicative set. Central set. So the kind of things that you can, is a set of central elements of R that is closed under multiplication, the kind of things that you can actually localize by. So that it makes sense to talk about this ring where you invert every element from S, look in R. So this is the ring of fractions of the form R divided by S, where R is in R and S is in S. Okay, with the usual structure. And I don't need to worry about on which side I put this S because S is central. So it doesn't matter if this is S inverse times R or R times S inverse. All right, so theorem. If F is a flat R module, then the localization is flat over the open. But actually, let's just say that F is flat over S inverse R. Okay, so how does it go? How do we prove this? Oh, just tired. Let me just prove something different that is much easier. Instead of worrying about this, sorry about this, let's prove something much simpler. S inverse R is flat as an R module. And I'm not going to be worrying about this and having an extra modular. So I just want to say that that's an example of so if I have U, which is the spectrum of S inverse R. Let's suppose that this R now is commutative. This sits inside of the spectrum of R. And this is an open set inside of a spectrum of R. It's a statistically open set inside of a spectrum of R. And this open is an example of a flat morphism. An example of flat morphisms. In the sense that this guy is a flat R module. So this, in combination with the lemma which is proven, would give you this statement that I was making about taking a flat module here and restricting it to the open. All right, so so let's prove this statement that S inverse R, and this is geometric, this is for commutative rings, but this is true for any for an arbitrary ring. So let's prove this guy is a flat as an R module. And so how do we prove that? We're going to prove that this guy here is a co-limit of R modules that are free. So S inverse R is a co-limit of free R modules. As an R module. Not as a ring, but as an R module. So the way you do this, you just build up a category with objects of this category. For objects of this category, it's just the set S. And morphisms in this category, if you have some S, so a morphism from S to T consists of an element S prime in S, such that S times S prime is equal to T. So whenever you have an S prime that satisfies that thing, you're going to say, well, that's a morphism from S to T. So now, of course, this is a category. The identity morphism is just the identity in the ring R. Actually, that's tricky. Do I want to put them in R or do I want to put them in S? Doesn't matter. Yeah, I want to have my units in S. All right, so okay, and the composition is just by multiplication. If you have a map from S to T, which is given by multiplication by S prime, and you have a map from T to W, which is multiplication by T prime, then the multiplication by the product of the two guys is a map from S to W. So this guy is compatible by compositions. So this is a well-defined category. Okay, so the statement is that we have a diagram of this category into the category of R modules that takes S and gives you R. And that takes S prime as a morphism, S prime as a morphism from S to T. And it gives you, well, it needs to give you a map from R to R. And this map from R to R is multiplication by S prime. So let's check that that's a nice functor. Okay? So I claim that this is a well-defined functor. And yeah, indeed. So if I have another map from T to W, which is given by multiplication by T prime, then the composition of the two morphisms is given by multiplication. So if I have some T prime, well, here T prime is my map from T to W. Then the composition of these two morphisms of T prime composed with S prime is multiplication by the element T prime times S prime, which is equal to S prime times T prime. And this is a map from S to W. And on the other hand, the composition of the two maps at the level of R modules is a multiplication by the two of them. Composition from here to here is multiplication by S prime T prime. So that's a well-defined functor. Okay, so I claim that the co-limit is the localization. So the co-limit over this category is of R is S inverse R. Well, let's check that for this guy to be a co-limit, then I need to have a map from each one of these guys to this co-limit. Okay? So remember, this is a diagram indexed by these objects in this category R. So let me put a little S here. So that means this R, just going to label it by S. And I have for each S, I have such an R S. So for this guy to be the co-limit, this by definition comes with a map from each RS. And this guy does as well. From here to here, it sends an element R here to R divided by S here. Now, if I have a morphism from this RS to RT, which is given by multiplication by S prime, so what I want is the map from here, well, let's say. So if I have a morphism from RS to RT, the map from RT to S inverse R is given by, well, let's take a guy here, R. You map it here by sending it to S prime times R, and you map it here by sending it to S prime times R divided by T. But the morphism S prime was the morphism that satisfied there by definition a map from S to T was such that S times S prime is equal to T. So that means that this is equal to S prime R divided by S prime S, which is equal to that. So this diagram commutes. So since I have this diagram commuting, the universal property of this co-limit says that I have a map this way. Actually, the other way around. It means that I have a map from here to here. Now, of course, that map has to be an isomorphism. Why? So, what's the inverse of that map? Well, I'll let you to think about what the inverse of this map is. But an element here is of the form R divided by S. And you can send it to the diagrams where you just put R divided by R in RS. So that's the obvious map, which is an inverse of this guy here. All right, so once you have this, then Tor S on the category of R modules, S inverse R with coefficients in any module, N. Well, this is a homology. This is Tor, coefficients in R module of a co-limit. N. And which checked that Tor commuted with co-limits. A couple of classes ago. So this is the co-limit of this. But these guys are free. So put now k, put now k, put now k, and this is equal to 0 if k is bigger or equal than 1, because Rs is free. So that means that Tor from this guy with coefficients in any module is 0 if k is bigger or equal than 1, and therefore that guy is acyclic, therefore this guy is flat. Okay. Okay, so we've checked that open embeddings are flat maps. Zariski open embeddings are flat maps. Other example of flat guys are going to be smooth maps. Anything projective is flat, so vector bundles are flat. And the last thing I want to do is to, now that we've checked that localizations are flat, let's check how does Tor localizes itself. So we have a ring R, and this time let's take it to be commutative. And let's take two modules, M and N. So what we know is that Tor Mn over R is an R module. And by being an R module, I can localize it to, well, any localization of R. Okay? And I want to study that localization. Okay, so the first thing to notice is that this structure of our module here is given as follows. So let's suppose that you have a morphism from M to M, which is multiplication by an element R in your ring R. Let's suppose that you have this morphism F. Just multiplication by this guy like this. So let's take a projective resolution. Of this guy. And what you could do is multiply by R in each one of these guys. And I claim that this is a map of complexes. Making this diagram commute. And that's absolutely obvious. Because all of these guys were map of these differentials here were in the category of R modules. And I'm using here that this ring is commutative so that I can just take it out. So by taking the derivatives here, grab an element here, multiply by R, and take the derivative is the same thing as take the derivative and then multiply by R. So this implies that the action of R, so this implies that Tor dot Mn, so you get a map from, well, if I have a map from M to M, then I get a map from this guy to itself, which is multiplication by R. Right, so if I have a map from, Tor was functorial. So if I have a morphism from M to M, then I get a morphism from Tor Mn to Tor Mn, and that map is given by multiplication by R. Okay, so we have the following theorem. So let's take P inside of R, a prime ideal. What I can do is look at M, localize it at P, look at N, localize it at P. Now these are RP modules, so these are localized at P. Yeah, I'm horrible to writing these letters. This is a prime ideal. So this is the localization of R near the point given by P, and these are RP modules. Again, R is commutative now. So what I can do is just look at the Tor over RP. And these are RP modules. Now, let's suppose that this is 0 for every P. Then Tor R Mn is 0. And this is an if and only if. This is the following statement, that if you grab a module, an arbitrary module over any ring, module M is 0, if and only if all the localizations over every prime is 0. So what you can do is grab the module which is given by Tor Mn. Okay, so this statement for M being this module, or as an R module, says that this guy, as an R module, is 0, if and only if the localization of this thing over primes over an arbitrary prime is 0 for every prime. Now what we just did, how do I compute the localization of this? I claim that this localization is this thing here. Okay, so I claim that so how do I compute this guy here? So this is Tor R M N localized at P. But localizing at P is the same thing as just taking the tensor product with RP of that R module. And we have this lemma that we proved that this guy is flat, is a localization of R over R. And we proved the lemma that said that I could just take this tensor product R by a flat R module by putting these guys inside. This is the same thing as Tor RP of M tensor with RP, which is MP, and tensor with RP, which is NP. This is the lemma that we've proven for commutative rings, that if we have a flat R module, which is also a ring, then we can just take the pullback of two things and turn the tensor product, or I can just take the tensor product first and then pull them back. Okay? So I'm doing the pullback by the map, which is just the inclusion of this open inside of R. Okay, so that's the statement. So I can check that a Tor is 0 when I'm looking over a commutative ring by looking near each one of the points, in each one of the prime points of the spectrum. But now, this statement is the same thing. Since inside of each one of these, since each one of these prime is included in a unique maximal ideal, that's the same thing as checking them on maximal ideals. And of course, the same thing happens here. So this is the same thing as Tor Rm. So this is now a local ring. Mn for M maximum. This is 0 for every M. So I can check that at each close point of R, of the spectrum of R, these tors are 0, then the original tor was 0. And I don't need to check about higher dimensional points in the spectrum of R. All right, so let's stop right there. I think I've covered all of this chapter in tor in that book. I don't remember if there was anything else that this guy did. Yeah, I don't think there's anything else. So next time, I'll just continue with Ext. Same book.